Yeah, okay. Today we're going to focus on the estimand. But before we get into estimand, I think it's important to know ANCOVA and the MMRM. Uh, Basically, I think for statistical analysis of clinical trial data, there's three data types. There's continuous data, discrete data, and time-to-event data. Among the three kind of data, I think the most widely used is probably the continuous data. So we start with continuous data. As a matter of fact, the discrete data and time-to-event data, there are a lot of publications and researches. So in my lectures, I will not touch on that. But I want to focus on the estimate mainly because from the continuous data, there is some kind of evolution over the years. As you know, the key date of the entire drug development is 1962. That was the Kefauver-Harris FDA amendment. And then from that point on, we start looking at clinical trials, and drug approval will be based on clinical trial results. And from that point on, we were dealing with the, like I said, continuous data, discrete data, and time-to-event data. And the application of the continuous data in clinical trials, of course, we start with t-test, and then we move into analysis variance, and we can look at like regression, analysis covariance, and then get into 21st century, we got into MMM. And so there's a little history behind the derivation of estimand. So let's start from the simplest case. So what we do in normal distribution, suppose we say X is normal distributed with mean, mu, and sigma squared. All right, so that's X. Now, if you want to look at the probability from any point to any other point, say you want to look at probability from here to here, or you want to look at tail probability from here to here, or tail probability from here to here, what you have to do, you have to do integration. You have to integrate from negative infinity to positive infinity of the normal function, or of course, depending on the cut point, you can integrate negative infinity to a particular cut point, or positive infinity to another cut point, or negative cut point to positive cut point, positive cut point to positive cut point. You have to do integration, so it's very inconvenient. So then, what people do is that in order to simplify it, what you can do is that you can take this thing they call Z transformation, X minus mu divided by sigma. So what are you doing is that X minus mu is for every point from here, subtract mu, right? So you're shifting the distribution to here to mean 0. And then you divide by sigma. You sort of standardize it to a 0, 1. So now we got Z is normal distributed with mean 0 and variance 1. So we converted from X to Z. Now this conversion essentially is sort of standardizing it so that now we can look up table. If every normal distribution can be standardized, then the probability coverage, you don't have to do integration. You can just look up table and you can find out the probability. So now this is Z equal to X minus mu divided by sigma. All right. So that's what we do. All right. We sort of standardize it into this form. Now, what is this? This is a signal to noise ratio. This is a signal, and this is noise, right? Signal to noise ratio. So the larger the numerator, the more likely to detect the difference, right? So that's your signal. Your signal is a numerator, right? If you have a large numerator, then it's more likely to detect the signal, right? Now, you sort of look at from z-test into t-test. Now, t-test is x bar minus the hypothetical mean divided by standard error, right? Now X bar follows this sampling distribution, so now you have a degree freedom associated with it. So now you got into t-test. And later we're going to talk about f-test or chi-square test. These are all sort of signal-to-noise ratio. Most of these frequently used tests are signal-to-noise ratio. So we can sort of move from z-test into a one-sample t-test. And then from one-sample t-test, we move to a two-sample t-test. So let's take a look at two-sample t-test. So this is a group of simulated data. So suppose I want to develop a drug to lower blood pressure. And the test drug lower blood pressure more than the placebo. That's my simulated data, all right? Now, I simulate these two group data, but if you combine them into one group, then of course you're gonna have a one sample t-test. The model is very simple, y equal to mu plus epsilon, all right? So you're gonna have a one sample t-test. Now for one sample t-test, what you do, you get x bar divided by standard error, right? Now, how do you calculate standard error? Standard error is now your sum squared for y, right? No, instead of saying x, I should say y, all right? So we have this is 100 observations, 50 on test drug, 50 on placebo. So out of these 100 observations, you're gonna have a y bar out of 100 observations. Now, if you take y bar, y minus y bar, y sub I minus y bar, square it, and you sum them up. So it's sum of yi minus y bar squared. And what you get a sum square of y, SSY, all right? So now we see SSY, right, for the entire 100 observations, SSY. That variability reflects the total variability of this data set, of this 100 observations. Now, if I take 50 of them on test drug and 50 of them on placebo, I look at how much blood pressure they're lowering. So test drug lowered maybe about 18, placebo lowered maybe about 6. So there's 12 millimeter mercury difference. And you perform this t-test, two-sample t-test, which is xt bar, this guy here, xt bar, minus xp bar, that's test drug, that's placebo, minus xp bar, divided by standard error, all right? So now, if xt bar and xp bar are very far apart, then you're going to see a clear statistical significance. But if xt bar and xp bar are very close to each other, so it's the same set of data, I re-randomize, I just look at randomly allocate to T or to T or to P, right? To T or to P. I just re-randomize them. So now I got these two groups. Well, I'm sorry, instead of X bar, I should say Y bar, right? YT bar minus YP bar, all right? So YT bar minus YP bar. Now in this case, because I randomly assign these 100 numbers, you're not going to see any significance, right? Now on the other hand, if I take the largest 50 observations and call them placebo, the smallest 50 observations, call them test drug. Of course, they're pulling apart, very far apart. So I want to still come back to this idea about this. When I look at one single sample, when I have all observations together, I have this SSY, all right? So the standard error, I mean, if you look at one sample T, is a SSY divided by n minus 1. SSY divided by n minus 1 is what? You see various, right? And then you divide it, and then you further divide it by your sample size, n, okay? And take square root of it. So that's your one sample t-test. Y bar divided by square root of SSY divided by n minus 1 divided by n. That's your one sample t-test. Now, if I look at two-sample t-test, okay, that's x t bar, y t bar minus y p bar divided by standard error. So let's take a further look at what the standard error is about. All right. So in a two-sample setting, you basically just have two treatment groups. You do a two-sample t-test. Now, if you expand it to three groups, and so once you have three groups, now I have three groups, right? Here I have 12 observations. Group 1, Group 2, and Group 3. All right. Now I got three groups, so you can no longer using t-test to handle it. So you move into f-test. So now you have three groups. You have the overall mean. That's the red bar is the mean of the 12 observations. And you have within group mean. All right. Group 1, you have mean here. Group 2, you have mean here. Group 3, you have mean here. Okay. So remember that SSY is now SST, right? Total sum squared. So total sum squared is regardless how many groups you have. If you take this as an entire sample, then you have the difference from here squared plus the distance here squared. You sum them up. That we got sum squared for total. Now you look at sum squared for within. For within is really about the variability. Is y sub ij minus y sub I bar. All right, that's within each group. So you have that sum square. All right, you have those four observations. You add them up. The square, you squared, you add them up. You squared, you add them up. You squared them, you add them up. Adding them together, that is your sum square for within. And this is your sum square for between. All right, it's group mean to the overall mean. Group mean to the overall mean. Group mean to the overall mean. So what you're doing, you're essentially breaking down the total sum square into the within sum square and between sum square. For two-sample t-test, it was the same thing. All right, you're breaking down into a between sum square and within sum square. But in t-test, because it's is on the linear level, where f-test is on the square level, all right, on the quadratic level. Well, we know that for an f-test, if the numerator degree freedom equal to 1, then f equal to t squared. So that's how you get the t and f relationship when you have only two groups. So what we're doing here, we're basically breaking down the total sum squared into two pieces, within sum square and between sum square. All right. Now, in the modeling process, statisticians add covariate terms, and these covariates will take away sum square, reduce sum square error. What I'm talking about is this table here. All right. Now, let's go back to a one sample t. Let's go back to a one sample t. If you go back to one sample t, you don't have any of these. All right, you don't have any of these. All you have is sum square for total, right? That's all you have with one sample t. And what you do is, of course, you take sum square for total divided by n minus 1, take square root, and then the numerator will be your x bar minus the hypothetical value, 0 in most cases, all right? So that's a one sample t-test. Now, if I have only one covariate of interest, which is treatment, all right? So in drug development, this is our main interest, all right? We're trying to see if there's any treatment differences. Two groups, test drug versus placebo. So this is only 1 degree freedom, all right? That sum square for treatment is what? It's x1 bar minus 2 bar squared, or y t bar minus y p bar squared. That is this, all right? Y t bar minus y p bar squared, that's sum square for treatment. Y t bar minus y p bar squared. Y t bar minus y p bar squared. So that is your sum square for treatment. All right. Now, if I'm doing a two-sample t-test, I don't have any of these terms. So all I have is sum square for total, sum square for treatment, yt bar minus yp bar squared. Your SSY minus that, the rest of them being your residual. Okay. And now the degree freedom, here's 1 degree freedom. SSY, I have n minus 1 degree freedom, n minus 1 degree freedom. And here is n minus 2 degree freedom, right? N minus 1 minus 1, you got n minus 2 degree freedom. So your sum square for residual, which is a difference between the total sum squared and the treatment sum square. So in other words, this is your SS between, and this is your S squared for within. And now you divide by n minus 2, you got mean square error. Now you have only 1 degree freedom here, so your mean square for treatment is equal to your sum square for treatment. That becomes your F test. All right. So what we're trying to do from a statistical point of view is, if you want to have a more significant test, what you do, all right, you either adding covariates or you increasing sample size. That's pretty much what we do. All right. If I add covariates, see, a center effect, a baseline effect, each one of the covariates is taking away some of the sum squares. Remember, the sum square for total, which is SSY, is not changed. For any given data set, SSY is not changed. If you keep adding terms as covariate into the model, it's just taking away some squares, so that makes your sum square error smaller because you have other terms or covariates trying to explain away the total sum square. And you say this model sort of explained these amount of sum square, so the rest of them being the sum square for error. I call it residual because that's the leftover. All right, everything else you can explain it with certain kind of covariates. So in drug development, we're looking at yt bar minus yp bar, all right? The test drug mean minus placebo mean, divided by the standard error. And if the drug is very good, then what happened? Now you're looking at this situation, extremely good. Then it doesn't matter how big your denominator is, because your yt bar minus yp bar is a huge value. All right, you have a big difference. It's easy to get significance. But if your yt bar and yp bar is very close, and you still want statistical significance, what you do, you increase sample size, right? Once you increase sample size, even very tiny differences, it's going to look at statistical significance. So in the modeling process, statisticians add covariate terms or increase sample size. These are the only 2 ways you can make the test more significant. We're dealing with continuous data, all right? You either increase sample size or you increase number of covariates in the model. And because these covariates take away sum square, so that reduces sum square error, it makes it easier to have a large F value. Reduces P value, you make the model more powerful. All right. So I want to bring up a point here that in drug development, phase 2, of course, phase 2 will be the key stage of identifying drug efficacy. But also at phase 2, remember the first phase 2 trial is a POC, proof of concept trial, right? So from a proof of concept point of view, would we like to have a powerful model? Let's think about this question, all right? Now from proof of concept point of view, what you really want is to have a big numerator YT bar minus YP bar. Right? If your first phase 2 trial, you're able to demonstrate clear efficacy. When I say clear efficacy, it's not about a small p-value. It's about large treatment difference, YT bar minus YP bar. Then you can make an easy go decision. Remember, in phase 2, we have only limited sample size. So there's not much we can do in terms of increasing sample size because most of the time in the POC study, your sample size is limited. So the point here from phase 2 perspective, because you're trying to decide whether the drug works or not, it has nothing to do with power. Power is only meaningful when the drug works. If you know the drug works, you look for power. But if you don't know whether the drug works or not, your decision can be type 1 error or can be type 2 error, right? It has nothing to do with power. Phase 3 is a different story. Because by phase 3, the company is committed because they see the drug works. So they want to increase sample size, make it 90% power, 95% power, 99% power, whatever they want to do because they are committed. They know the drug works. They're going to increase sample size to make sure the drug works, or to demonstrate the statistical significance. But phase 2 is a different story. Phase 2, we should not be looking for power. Phase 2, what we should look for is robustness. Right? What is robust? 2 sample t-test is robust, good enough. Do you really need this additional covariate? Yes or no, or maybe. But the key of phase 2 is how big your numerator is, regardless of the denominator. So now, if you're in phase 3 and you're doing submission, you propose this model. All right, by the way, the model is written this way. All right. All right, your treatment effect, your center effect, your baseline effect. All right, when you write this model out that reflects this model, then that's your main effect of interest. The center and baseline are, in a way, nuisance parameters. You're just introducing these parameters or these covariates into your model with a hope that could residual sum of squares. Of course, it has some other meanings because if it doesn't have any other meaning, why should we include these extra terms? Because simply including more terms, we are artificially reducing the sum of square for residual. So if you're at FDA, when you want to approve a drug, what do you care? You care about numerator. You don't really care about denominator, right? So adding more terms doesn't make sense. Simply making the p-value small, it does not make your drug approvable, right? The drug is approvable mainly because the YT bar minus YP bar is large enough, all right? So by adding more terms doesn't help you. Now the regulators, I mean FDA, EMA, globally, they understand this trick. So they said in the phase 3 trial, the main effect, of course, the primary interest would be treatment effect. The only other terms can be added into the model are stratification factors and baseline. All right, let's look at this. So treatment effect is the main effect that we're interested. So if I design a trial, I have to have the treatment effect. Now, this, instead of looking at it as a center effect, we should consider it as a stratification factor. All right. So why is a stratification factor acceptable in a primary model? Because stratification is a design practice, all right? It's not sort of data-driven, all right? The difference between design phenomena and data-driven phenomena is that at design stage, you didn't see the data yet, all right? But you decided to stratify. So instead of looking at synergy effect, let me look at it as gender effect. If you stratify by gender, then you're allowed to put this covariate into the model. If you did not stratify by gender, you should not. All right. Now, why did people always say synergy effect, synergy effect? It was in the traditional way, when you do block randomization, you ship drugs in a block. All right. So a block of drug goes to center 1, a block drug goes to center 2, and so on and so forth. On that basis, you're naturally stratifying by center. But we know things are changing now. We're doing kind of IRT, we're doing global trials and things like that. So you don't necessarily have to ship drugs by center. I mean, even though you ship drugs by center, it's no longer based on center, no longer based on block randomization. So synergy effect is not a big deal now. But stratification can still be of concern, because at the design stage, when you thought about this factor being an important factor, you're willing to stratify it. Now, stratification is introducing logistic difficulty. All right. So without stratification factor, you can just simply randomize, right? The patient coming in, we randomize to A or B or to whatever according to your protocol. But stratification is that you have to first look at this patient's characteristic. Like if you stratify gender, then you have to look at their gender. If you stratify by age, you have to look at their age. And then you randomize within that strata. So stratification, you're introducing a level, an additional level of difficulty in operation. And also, by introducing any additional process, you're subject to a potential error. All right. Now, many of these randomization error, you only find it after blind is broken. After blind is broken, you look at it, whoa, this patient was a male patient, but we stratified as a female. Or this patient was a young patient, but we sort of stratified as an older patient. So you're more prone to errors, to mistakes, and things like that. So for design characteristics, we're paying the price up front. And so that is justified to have this term in the model. Okay. So we explained tau is important because that's why we designed this trial. Gamma is important because we stratified on that. Now, Xijk is the baseline value for this subject. So here, this is y sub ijk is change from baseline of case subject in JS center receiving ICE treatment. So IJK, all right. ICE treatment, JS center, case subject, and this is the residual corresponding to that. All right. Now, I want to spend some time to explain this baseline covariate. How come we can incorporate this one into this model? All right. Now, the first thing we want to look at is the analysis can be based on the last observation, Zijk, or can be based on Yijk. All right. Now, if we're low blood pressure, this patient's baseline blood pressure is 170, and no, baseline blood pressure is 170, and after 4-week treatment, it reduces to 150. 150 minus 170, you got minus 20. So that's the response variable you analyze. Or you can analyze 150 instead of analyzing minus 20. All right, so this you analyze with minus 20, the treatment difference. I mean the difference between baseline and endpoint. All right, or you can just analyze the endpoint, the week 4 value or whatever, right? Now, if I do not have baseline in the model, if I do not have this term in the model, then these two analyses give you a very different treatment effect, right? Because the mean is already different. This mean is a negative value. This mean is a very high positive value, right? I mean, week 4, blood pressure can be from 120 to 180 or anything like that. So the mean may be 140. This could be minus 10, minus 5, minus 8, minus 15, right? And of course, you have a mean, and then your treatment effect, your stratification factor effect. I mean, these values are very different. What I should have done is I should say mu prime, tau I prime, gamma j prime, and whatever, all right? So if you don't have baseline in the model, then the treatment effect could be different depending on whether you're analyzing change from baseline or analyzing the last observation, all right? But if you introduce baseline in the model, now it's different because remember, Zijk is Xijk plus Yijk, right? Zijk equals to Yijk plus Xijk. So Zijk being Yijk plus Xijk, so you just do this. So now this coefficient becomes beta plus 1. And in that case, your treatment effect estimate is the same. So if you introduce baseline in the model, then whether you're analyzing the last observation or you're analyzing the change from baseline to the last observation, your treatment effect is not changed. Okay, so that's the first reason why we can include Xijk in the model. Before I go any further, I just want to clarify on the terminology. Traditionally, I mean, I went to school in the 70s and in the 80s. And at that point in time, we call the models the following way, all right? If your covariates are all discrete, we call them an ANCOVA model, they're not spurious, all right? If your covariates are all continuous, we call them regression analysis or multiple regression. And when your covariates, including both discrete and continuous, we call them analysis covariates. Okay, now if I take this as a continuous variable, right? If I take this as a continuous variable, now this is actually a linear regression model. All right, the linear regression with all these intercept values, and this beta is a slope associated with baseline. Okay, so if I analyze the change from baseline, so I'm looking at this as a negative value, all right? So y sub ijk being changed from baseline. We're looking at blood pressure, for example. And xijk is my baseline blood pressure, all right? Now, suppose I do a plot where x-axis being baseline, y-axis being changed from baseline. So I'm going to see many data points on this graph. Now, the first question is that should I anticipate a negative slope or should I anticipate a positive slope? So in other words, is beta going to be negative or positive? So the way you think of it is that if I have very high baseline, 180, 190, I have very high baseline, then my change can be large, can be minus 30, minus 40 or something like that, right? So I have very high baseline, the change is large. If I have very low baseline, like 130, 140, 130, 140, my change will be probably 5 or 10. So it's around here. So now we can anticipate the slope is negative. Okay, so this is your slope. This is your baseline measurement and the slope. So remember, this xijk is corresponding to this y sub ijk, which is this is that patient. And this is the value of the patient. It's the baseline value of that patient, the change from baseline value of that patient. So for each individual, there's a data point, all right? At xijk and yijk, there's a data point. So we can do a regression, all right? Now here, these are just your intercept, right? Gender 1, gender 2, different intercept, treatment 1, treatment 2, different intercept. Okay, so let's take a look at this graph here. Now, in this case, I have X being my baseline, Y being change from baseline. So like I said, it's a negative slope, all right? The test drug lowered more blood pressure than the placebo did, right? So you have all these patients are placebo patients, all these patients are test drug patients. Suppose I do not have X as a covariate. So I go back to the original model. I did not have baseline as a covariate. So then I will not have this dimension. I will not have x-axis. So now all these data points are going to fall on the y-axis. If I did not include baseline as a covariate, so all these data points are going to be here. And now if you look at all the blue points, the placebo mean is about 10. If you look at all the red points, the test drug endpoint, the test drug mean change is about 0. Okay, so the treatment difference is about 10, right? If you look at these data without including baseline as a covariate, so this group of data will have a mean 0. This group of data will have a mean 10. So the treatment benefit is how much? It's about 10 units. So by taking test drug, you're lowering about 10 millimeter mercury of blood pressure than taking placebo. All right, so that is when I did not include baseline in the model. The next thing is that if I include baseline in the model, now I have this relationship, right? I include the baseline in the model. Now, what is my treatment effect? Now the treatment effect reflects on your intercept, right? It's about 20 to 10. So it's about the same, all right? So if I include the term in the model, now I'm looking at this, the tau I difference, right? But if I did not include it, if I don't have this term, then I have just overall test drug mean minus overall placebo mean, all right? But in this case, either way, I have the same difference, all right? So without including baseline in the model, I'm looking at the difference between 10 and 0. I have a difference of minus 10 units. By incorporating X into the model, I'm having a treatment difference about 10, right? Now, if you look at this data set, if I do not include baseline in the model, then the test drug mean is about 5. The placebo mean is about 5. There's no difference, right? If I do not include X or baseline as a covariate, so I'm just doing analysis of variance without baseline. What kind of treatment effect do I have? 0, right? Test drug mean and placebo mean is about the same. All right, both are at about 5 units. So test drug equal to placebo mean. Now, if I incorporate the baseline in the model, of course, then you're going to have the intercept. So because the two lines are parallel, so we can just look at this point. All right, if you look at this point, this is the difference. The difference is about 15, right? And it's about 10. It's about 10. The difference is about 10. So it's about 5 here. It's about minus 5 here. So we have difference about 10 units. So what's going on? Let's look at this data set. This data set, including baseline in the model or not including the baseline in the model, no difference. But in this case, including baseline in the model makes a difference. not including baseline in the model, you don't see any treatment benefit. What happened? All right, let's take a look at this data set a little bit more carefully. Let's look at the x-axis, the baseline. So in this data set, the placebo patients has a higher mean baseline. The test drug patients have a lower mean baseline, right? And you say, this is a randomized clinical trial, so by randomization, their baseline should be balanced. Yes, the baseline should be balanced. But what if you're just unlucky? You have all the high baseline patients into the placebo, not all, most of the high baseline patients into the placebo, most of the low baseline patients into the test drug. It could happen. When it happens, by including baseline in the model, you're adjusting this baseline imbalance. Of course, baseline imbalance can happen this way also. All right. In this case, if you do not include baseline in the model, the test drug mean is about 0, placebo mean is about 10. If you do not include baseline in the model, there's a clear difference, about 10 unit difference. But once you include baseline in the model, there's no difference. All right. So baseline imbalance could happen in so many ways. And at the design stage, we did not know whether we're going to have balanced baseline or not. So we incorporate baseline as a covariate in the model. All right. So there are two reasons why we incorporate baseline in the model. The first reason is that by incorporating baseline in the model, then whether you're analyzing the change from baseline or you're analyzing the last observation, your treatment effect is not affected. The second reason being, by adjusting for baseline, you can adjust for potential imbalance. The third reason, of course, is by introducing baseline in the model, help you reduce the residual sum squares. So given these three reasons, baseline can be incorporated in the model. So if you read IPHE9, which is the statistical principle for running clinical trials, is that the acceptable terms in your model for the phase 3 analysis are treatment effect, stratification factor, and baseline. No, nothing else. All right. In other words, additional terms are not justified to be included in the model. Why? Because this model has to be finalized before we break blind. All right. So this model is a design feature. It's not a data-driven feature. After breaking blind, you look at the data, you say, whoa, gender is important, even though you did not stratify it. And you include gender in the model, you got statistical significance. And that kind of significance cannot be acceptable because it's a post hoc, it's data-driven. But from design stage, you haven't seen the data yet. If you consider stratify, then these terms can be included in the model. Right. But you don't necessarily have to include that in the model. Let me give you an example. All right. Nowadays, if we're still doing block randomization, many trials are doing that. You're still doing block randomization, and you ship drugs based on block. You do that. Then you're justified to have center effect in the model, right? Because you stratify by center. But many trials, they do not include center in the model for the analysis, which is okay. Why? Because oftentimes the amount of sum square taken away by center is not that much. So what? They're taking away a lot of degree freedom. So by including center in the model, you may increase your mean square error because you're losing degree of freedom, right? So that's why we have this model written this way, because these are the only two allowed covariates. And the next question is, why is treatment by stratification factor, treatment by factor interaction is not in the model? How do we write this interaction? It's tau gamma ij, right? Tau gamma sub ij. How come tau gamma ij is not in the model? All right. So from hypothesis testing point of view, there should be no model selection. That's very important. All right. You have to, the primary model has to be well specified before you unblind for your phase 3 submission trials. Okay. If you allow model selection, there's potential alpha inflation. So we should not select model. An analytical model should be completely pre-specified before breaking blind. Most robust test is permutation test. T-test approximate permutation test. So if I were designing the phase 3 trial, I'll probably just use a permutation test or use a 2-sample t-test. Good enough. These tests are very robust. All right. I don't need any other terms in the model because the drug is good. Now, just in case the drug is not good enough, okay, so we include some additional covariate in the model. All right. But whatever covariate you want to include in the model, it has to be justified. It has to be clearly, completely pre-specified. ICHE 9. The recommendation for analysis of continuous data to say two sets of covariates are acceptable: stratification factors and baseline. Because stratification is a baseline practice. At the design stage, you've considered about stratification, so that's acceptable. And reasons why baseline covariate can be acceptable, I'll give you 3 reasons. One reason is analyzing Y or Z without changing your treatment estimate. The second one being you can adjust for baseline imbalance. And the third reason is that you can reduce the subscribe for residual. All right. All right. Now, what is treatment by factor interaction? So treatment by factor interaction is to treatment effect different at different levels of the factor. Right? For example, is the test drug better in male and worse in female? If the test drug is better than placebo in both male and female, there's no interaction. Of course, there's other factors, region, background, medication, smoking status, and all those kind of stuff. So let's just look at what does it mean by treatment by sex interaction. Okay. Now, if I have 2 treatment groups, test drug and placebo, I have male and female, I have now a total of 4 subgroup means, right? I'm going to have placebo, male placebo mean, male test drug mean, female placebo mean, female test drug mean. All right. Now, if there's no treatment effect, there's no gender effect. All right. So the 4 subgroup means are the same. That's very clear, right? There's no treatment effect, no sex effect. Now, what if there's treatment effect, there's no sex effect? Treatment effect, no sex effect. All right. Test drug is better than placebo in both male and female. Clearly treatment effect, and there's no sex effect. Now, what if there's sex effect but no treatment effect? We see this. All right. Male effect is higher than female in both test drug and placebo. There's sex effect, but there's no treatment effect. What if we have both? All right. Now we have both treatment effect and sex effect, but there's no interaction. Right. So in this case, without interaction, your treatment benefit for male and treatment benefit for female is the same. All right. Although your male effect is higher than your female effect, but the treatment difference are the same. So there's no interaction. And of course, statistically speaking, these are what we call parallelism. And we clearly see parallelism. Once they're parallel, there's no differential effect across sex. Now, here's what we call quantitative interaction. That is The test drug is better than placebo in both genders. All right, test drug is better in male, better than placebo in male. Test drug is better than placebo in female. But the benefits are different, so we call it quantitative interaction. And this is qualitative interaction, that the benefit on one gender becomes harm on the other gender, right? So test drug is better than placebo, but worse in male, but worse in female. Okay, so that's what we're talking about, interaction. All right, now let's go back to this model. Why there's no interaction in this model? All right, why there's no interaction? Tau gamma IJ, why there's no interaction in the model? The first thing is that from design point of view, you do not expect there's interaction. All right. If at design stage, I think there's a treatment by gender interaction, and the drug is only better for male, but not that much better for female, then it would be not ethical to recruit female patients. Because I already know that. All right, I thought the treatment is only beneficial for male. Then it's not ethical to recruit female. Now, if my design is including both male and female, that means I assume there's no interaction. All right. Now, the fact is that at the design stage, you didn't see the data. What if you see the interaction after blind is broken? Then you perform treatment by gender interaction as an exploratory analysis or as a sensitivity analysis. But that's not your primary analysis, because at the design stage, you don't anticipate there's interaction. So that's the first reason. All right. The second reason is that if you have interaction in the model, if you go back to the statistical textbook says you first test to see if there's interaction. So you have the model including interaction. And the interaction is not significant. You drop the term, you have a main effect model. Now you have two models. One model including interaction, the other model does not include interaction. There's a model selection issue. Now, which model should we believe? Your alpha is inflated because you're introducing model selection. Right? So the second reason why tau gamma IJ is not in the model is because in clinical trials, there's no space for model selection. So that's the second reason. And the third reason is that how are you going to test interaction? Remember, when you calculate sample size, the sample size calculation was based on treatment difference. It was not based on interaction. So from the sample size calculation, you did not allow any alpha for interaction test. In other words, if I came up with an interaction test p-value of 0.06, what does it mean? Is it significant? Is it not significant? I don't know. I did not allocate any alpha for it. Right? So for these three reasons, the tau gamma IJ should not be in the model. Another question would be, what about baseline by treatment interaction? The first question is that how do you express that interaction? Remember, if it's treatment by factor interaction, we can look at a tau gamma IJ. But the treatment by baseline interaction, you don't add another term to it. All you have to do is the subscript beta I. Beta I now is a heterogeneous slope model. Okay. So if the two lines are parallel, this means there's no treatment by baseline interaction. No treatment by baseline interaction. Two lines are parallel. All right. And the analysis is very straightforward. I'll say the treatment difference is this much, right? You simply subtract, you look at the intercept, right? You look at the difference in intercept. There's 5 unit difference. That's all you have to say. I mean, that's how you label the drug. Now, but if you include treatment by baseline interaction in the model, now you're looking at a heterogeneous slope model. Your beta 1, beta 2 are different. Now, what you're looking at? You're looking at this case, right? Now, the test drug is better than placebo when you have very high value of test drugs. This is super better. But when you have very low baseline, placebo is better than test drug. Then how are you going to label your drug to say the test drug is better than placebo by how many units? So the general agreement is that if you look at the baseline mean, so this is X bar across all treatment groups, baseline mean. If you look at baseline mean, you look at this difference. And you report to say the treatment benefit at baseline mean is this much better. And then you can label the drug. Now, the question is that when you run SAS will give the intercept when X equal to 0. So when you run SAS, you include this model, SAS will give you this difference. But this difference is not what you want. You want this difference. So how do you trick SAS to give you what you want? So you just subtract the baseline mean of all baselines. And you just shift these 2 lines to here to be 0, and they'll give you this. So that's how you write that model. All right. So for heterogeneous slope model, you write it this way. Okay. Now, one final note about this model is that all these terms are considered fixed effect. The only random effect is residual here. All right. Now, treatment effect is fixed effect, there's no doubt. Baseline effect we consider fixed because when you look at regression, you're looking at the X, the covariate being fixed. Now, what about this? If this is center, should we consider center effect, fixed effect, or random effect? What's the difference by treating an effect as a fixed effect or random effect? The difference is that about generalizability. If I want to generalize my results across all possible centers, I say I randomly choose a few centers and I observe these. Then I consider it as a random effect. I want to generalize it. For fixed effect, if I'm just recruiting patients from the 3 centers, I'm just my conclusion is just for these 3 centers. Now, how to look at this point is a philosophical view. All right. From the company, our job is to report all the findings honestly to the regulatory agencies. So we have treated it as fixed effect. We're not in the position to generalize it. On the other hand, FDA, after looking at these results, they want to generalize it. So they may consider that as a random effect. So we'll stop here today, and I hope I have a good introduction about what this ANCOVA model is about in clinical trial analysis. Thank you.